And finally, I want to talk about unsupervised question decomposition for question answering because the previous lecture, that lecture from Washington University, some people argue that it is really very much similar to rule base. It's lots of heuristic, because the complexity of human knowledge, I mean natural language, is that it has many cases. For this case, you should do that. For that case belongs to a question. It is bridging. It is intersection. It is what was else, for example, comparison. But you say, but people in Facebook or big companies like Google and Microsoft, the three companies, they want something that is scalable. They don't want to get involved with something that needs a lot of cases and makes their codes buggy, and they want a simple solution, and they want to use their powerful GPUs, which is their advantages. So that's why they created this algorithm, unsupervised question decomposition. So we first use this unsupervised idea to see the similarities. And this is just a pseudo decomposition. It's not perfect because it is not related to the topics of the original question. So we go there and we try to learn it, but it's not supervised. The interesting thing is that it is not supervised. So they propose two algorithms, onus and sequence to sequence. And you could do it either onus or sequence to sequence. And finally, after decomposition, after you decomposed your question into a set of questions, then you recompose. So you answer them and then you recompose and you get the final answer of the original question. And this is the overview of Hotspot Qa. So for each question, Hotspot Qa provides 10 context paragraphs from Wikipedia. 2 paragraphs contain question-relevant sentences called supporting facts, and the remaining paragraphs are irrelevant. They are distractor paragraphs. They are not related to original question. And what is onus? I summarized in just 3 steps. I first create a noisy pseudo decomposition for each hard question by just embedding similarity. It's so easy. We just find, if you remember, clustering, k nearest neighbors, those sort of things. But we do it more efficiently. So after that, we train a decomposition model on the mined data with unsupervised sequence-to-sequence learning, allowing onus to improve over pseudo decomposition. As I said, these pseudo decomposition in step 1, they're very noisy. They're not related to topics of the question. So we want to use a language model. For example, masked language models, beautiful, because you have already encoded all the complexity of English language or any other language in this model. So we are not worried if we don't know how to substitute appropriate word, because we already know the questions we can do in the first step. But here we try to remove noise and make the question more appropriate with better words. And finally, you validate onus and multi-hop question answering with questions require reasoning over multiple pieces of evidence. So simple questions goes to single hop. We know it's so easy. Everybody can do it. But for hard questions, we give it to a multi-hop module. So it's a multi-hop problem. So when I say hard question, I mean it needs multi-hop investigation. So we train a multi-hop question answering module M by maximizing this log probability. what is the probability of the answer, given that you know the context, several paragraphs in this case, and your question. But the easier objective is to decompose it, say that, okay, this is the sub-question 1, sub-question 2, and sub-question n. The answer, the sub-questions and the answer. Because if each sub-question has a sub-answer. And so this is the easier objective. And because supervised decomposition, you need to know the pair. What is this for any, what is the decomposition? So it's too expensive for human. So there are 3 approaches. We map a question into sub-questions using this unsupervised technique, and we find sub-answers. So we have this question S, we have this sub-answer A, and then we use S and A to predict A. These are just sub. But this answer is the answer of the original very complicated question. So it's just 3 steps. We map it. As I said, it's pseudo decomposition. We map a question into sub-questions, and then we find sub-answers A1 through AN with single up QA. And finally, we use those sub-questions and sub-answers to predict the answer of the original complex question. So we divide or separate the corpus into 2 corpuses. So the first one is hard question corpus called Q. The other one is simple question corpus called S. So this is single hop, this is multi-hop. And as I said, the first pseudo decomposition is easy. We are just maximizing this F. But this metric F, we use as an inner product. I think here. Yes, it's here. We just use the inner product. And because we want to say our question should be very similar to the sentence, the sub-questions. But on the other hand, your sub-questions should be very different to each other. We don't want them to be redundant. We want them to be very, let's say, they are negative examples. They are very dissimilar. And we are learning to decompose. So this is F, and so we use pseudo decomposition. So we have 2 approaches. We either use sequence to sequence or unsupervised sequence transduction. So we learned from Q to D. As I said, a good or simple way to define F is just this inner product. V transpose, question transpose, sub-question 1. Question transpose, sub-question 2. Sub-question 1 dot sub-question 2, because it's just inner product. And so we have found our sub-questions using this. But it's so complicated, that's why we use the approximate solution. So what do? We just find an approximate pseudo decomposition over top K of these, of this one and this one. Of course, n is here 2. It means we have two sub-questions, but you could have question 1, question 2, question 3 for a given question Q. But here, for simplicity, we say n is just 2. So we have only 2 questions, 2 sub-questions. And we maximize it over top K, VK transpose VS, because this is the main factor of this optimization. And of course, we use random retrieval in the algorithm. I will show you when and where. But it is for comparison, we test the random pseudo decomposition. So we retrieve these S1s by sampling uniformly and editing them. There is a good article how to you edit that to create more appropriate and something related to the context, some words related to the context. So what is a masked language model? Because we need it for the second step. Just a quick recap, that masked language model, so we mask some words. So this is the language model. We mask some and then we predict them. So it provides a very good embedding of the structure. So I think a good example is all the very best. We predict very, or here we mask two. And in general, we try to mask around, it is suggested in the papers, 12%. Here I've written 50, I think it's either 15% or 12%. Some people say 12%, some people say 15%. So we mask around this. This is the good result because people have experienced that. And so we use paired tokenizer. We want to know what is the idea of each of these, because each word is a long vector. We just need to know the idea of that. So we use tokenizer to first separate and then see which ID belongs to which word. Even this word mask has an ID, is preserved. And so we use pre-trained model. You could use it from anything in Hugging Face that you like, and then you are ready for the mask model. So as I said, this is the simple pseudo decomposition. And finally, step 2 is, so we are inspired by this article, cross-lingual language predicting. So not only we have the English words, that we want to see if it is masked, what is the answer, so we predict its language model, but also it is multilingual, it is cross-lingual, because we are also using French words. So we are also masking French sentences to see the answer. So inspired by this one, they created this algorithm. So we say we have a noisy question. We have decomposed that. We want to see how can we mask them and then find the better decomposition with luckily better algorithms. With hopefully better algorithm. So this is the fine-tuning, and we want to improve over. So the goal is just improvement over pseudo decomposition, because we already have the questions, but their topic words are not appropriate. And then we do recomposition model. We know the answers of the question, we recombine them, and then we get the final answer. Another good article that I highly suggest is generating sentences by editing prototypes. So we are given a sentence. So this is an article, I don't have time to explain it. Another good article is this one. Select, answer, and explain. Select, answer, and explain. I mean, the title answers. So I summarized it in just one slide. So it's not only the question, but the way you try to solve it.